For business and industry, the Pennsylvania Technical Assistance Program presents Looking at Materials. Today, ceramics.
The word ceramics generally leads people to think of art classes, of pottery, of vases, of porcelain sculpture, and fine china. These images are all quite valid. These articles are ceramics, and the artists and craftsmen made them by simple ceramic forming processes. But pretty as they are, they have very little to do with ceramics in the sense in which the modern materials scientist uses the term. They envisage quite different uses and accordingly make quite different demands on the material. To the material scientist, the essential features of a ceramic are its composition, the high temperature processing by which it was formed, and the internal architecture of its constituent parts. Now, some of the special features of this internal microstructure can be seen in a microscope if we look at the surface of a suitably polished ceramic specimen. It is clear that the material is heterogeneous, with a structure of tiny crystallites or grains, sometimes with closely fitting grain boundaries, sometimes with an amorphous or glassy matrix between grains. Often there is more than one type and composition of crystallites. This dense, rather strong structure of interconnected crystallites is formed by high temperature firing. In conventional ceramic processing, the chemical raw materials are first reacted to give the required composition. The reacted material is then milled to a very fine powder. And this is compacted, usually with some organic binder, to enable the pieces to hold their shape. The objects are then heat-treated, during which interdiffusion and sometimes local melting bonds the powder grains tightly together. By careful control at each stage of preparation, the ceramic engineer can modify the final microstructure of the ceramic and tailor its properties to a wide range of industrial application. For instance, the very high compressive strength of some compositions makes ceramics useful for structural materials. The hardness and stability of glazed ceramics makes them clean, hygienic, surfacing materials. The steel and glass industries are completely dependent upon the thermal stability and resistance to chemical attack of refractory ceramics, which are used to contain their high temperature, molten, raw materials. The extreme hardness and abrasion resistance of some ceramics is providing new tools for the metal cutting industries. With these hard tool tips, the metal can be cut so quickly that it comes off as a molten ribbon. Ceramic studs also are providing new safety features in your auto tires. Ceramic fibers, when embedded in a continuous matrix, form a very light, extremely strong composite material. The electrical and electronics industries are insatiable in their demands for new and better materials with many special properties, and again, ceramics play a vital role. To take just one example, one or two examples from the many possible, millions of tiny ceramic magnets provide the rudimentary brain of most large digital computers. And larger ceramic magnets have long provided the deflection system which writes the picture onto your television screen. Other magnetic ceramics are rapidly replacing metal magnets in small domestic appliances, providing lighter, more compact, and cooler running electric motors. In electrical uses, ceramics run the whole gamut from the very large, high-voltage insulators which carry power into every community, down to the very tiny ceramic capacitors which occur by the dozen in every radio and television set. Now, spurred by the demands of these several multi-million-dollar industries, the technology of ceramic materials is developing and diversifying very rapidly. And of course, it isn't really possible to give a balanced account of the many interesting new developments in all these rather diverse fields within the short time which is available at our disposal. I should like to concentrate on just one topic to show how a new ceramic forming process is providing new materials with optical properties that couldn't be achieved at all before. The technique itself may have wider applications and could produce quite dramatic improvements in other ceramic properties. But first, we must take a look more carefully at the optical properties of conventional ceramics. Let's go into the laboratory where we have the necessary demonstrations set up. This pure magnesium oxide ceramic is a typical example of the products which result from conventional ceramic processing. If I hold it up to the light, you can see that the surface has a nice bright milk white appearance. If I hold it over the light, the source is obscured, no light is transmitted, the ceramic is quite opaque. This opacity is not due to light being absorbed in the individual crystallites of the ceramic, for a single crystal of magnesium oxide is quite transparent. It is in fact due to reflection and scattering at all the little internal surfaces which exist in the conventional ceramic. The effect is shown diagrammatically here, where everything has been scaled up enormously. Each internal surface reflects back or scatters a little of the incident light. And in our ceramic, there are so many surfaces that after only a very short path in the body, the incident beam is completely lost. This scattering process can also be demonstrated by a very simple experiment. If I fill this glass beaker with ordinary glass beads, I generate many internal surfaces, and when one looks through the beaker, it is translucent. The printing underneath can't be read. If now I pour into the beaker a liquid whose optical properties very closely match those of the beads, the liquid fills all the voids between the beads, and the system again becomes quite transparent. You can read the printing underneath the beaker. There are just as many internal surfaces, but because the liquid wets the glass, these surfaces are now in close contact, and it seems that they don't scatter or reflect the incident light beam. This simple experiment would suggest that if by some means we could make a very pure, very dense ceramic in which all the grains were forced into very close contact, then the material might become transparent and transmit the light beam. The crystallites of a ceramic, like magnesium oxide, are hard and brittle and do not readily deform, but the required densification has been achieved quite recently by a process called vacuum hot pressing. Now, to see how this process is applied, and to have a look at some of the fascinating properties of transparent ceramics and the devices which can be made from them, let us visit the Apparatus Division laboratories of the Eastman Kodak Company in Rochester, New York. There we'll talk with Mr. Edward Carnell and his team, who are skilled practitioners in this technique of vacuum hot pressing. I have been propounding the thesis that density is the key to good optical properties in ceramic materials. Could we have a look at the set of samples that you have that demonstrates this point very clearly?
Surely, I'd be delighted to show you some of our work. Here, for instance, we have a set of magnesium oxide samples which are all prepared from equal weights of the same starting powder. By this I mean we have taken a volume of powder like this and reduced it to a sample of this thickness. To demonstrate how the volume is reduced and the density increased, all the samples are of the same diameter, so that the height of each sample gives a good quick measure of its volume. Starting here at the left is some loosely packed powder. The overall density is only 30% of the magnesium oxide single crystal. Next is some cold pressed powder. This was put into a mold and subjected to 10 tons per square inch pressure. Its density is about 40% of the crystal density, rather higher, but of course still not very good. By heat treating the powder, as one would in conventional ceramic fabrication, we can obtain a rather large increase in density. This sample here is about 96% dense. It is quite strong mechanically, but on the other hand, as you can see, it is still quite opaque. To go much above 98% density, we have to use vacuum hot pressing. These samples here on the right were all prepared using this technique. As you can see, at densities of 98%, the samples begin to become translucent. And at densities of 99.96%, the samples are very clear and transparent.
I think this sequence demonstrates very beautifully how, with increasing density, the transmittance is increased and the scattering is reduced. Could you show what the microstructure is in one of these very dense samples?
Yes, we've taken many electron micrographs of fractured surfaces of these dense specimens. This particular photograph is at 35,000 times, so each grain is only 40 millionths of an inch in diameter. But you can see, even on this very fine scale, that the individual grains are perfectly mating.
Now that we're convinced of the effectiveness of this process, how does it actually work?
This method is really quite very simple in principle. The very pure, extremely fine powder with which we start is loaded into a die, which has a single mating plunger. The powder is cold pressed, and the loaded die is put on top of the apparatus. The die is now surrounded with a vacuum jacket and the top enclosure added. The air is pumped out and the die is heated. Pressure is applied to the plunger by a hydraulic ram. And after a suitable time temperature pressure cycle, the assembly is cooled and the hot press sample removed.
What sort of temperature and pressure is required?
This would vary with the particular compound we're using. However, in the case of magnesium oxide, we use a temperature of 1650 degrees Fahrenheit and a pressure of 10 tons per square inch. Well, let's look at a cross-sectional diagram of a typical pressing apparatus. Here you can see the individual components of a simpler model: the die, the plunger, the vacuum jacket, and the water-cooled top and bottom enclosures. Pressure is generated by means of the hydraulic ram and transmitted down through this plunger assembly, while high temperature by induction heating the die directly with a radio frequency coil.
Why is it necessary to take the air out of the work chamber?
Well, the vacuum serves two important functions. Firstly, it protects this die metal from oxidation. This particular metal would literally burn up at these high temperatures. And secondly, it helps remove the adsorbed gases from the surfaces of the powder. If these gases are not removed, they could be entrapped and form bubbles, which would cause light to be scattered, and the sample would be opaque.
Could we now take a look at some of the actual hot pressing equipment?
Certainly. Let's go downstairs. In the early days of our process development, we did all our initial pressing with this simple 10-ton carver press. It's quite a favorite of ours, so we had it brought down here just for this tour. As you can see from the size of the dies, we could only make samples up to about 1 inch in diameter. However, these were quite adequate for test purposes. Here I have the first piece of transparent ear tram material we ever made.
I know when I was here before, you showed me pieces up to 8 inches in diameter. What do the presses look like for such samples?
Here we have a 500-ton press, which is used in the production of larger pieces. But here is Dick Clark, who's in charge of production, and he can tell you how it works.
Well, it certainly looks quite a step up from the carver press. Is it really very much more complicated?
Not really. You see, a major part of the time in hot pressing is taken up just bringing the sample up to temperature before pressing and cooling it down afterwards. It would be uneconomic to tie the press up while these operations go on. In this equipment, we have 3 separate mold units. This one is heating up. The one directly under the press is under pressure. And on the other side of the room, a 3rd unit is cooling down for unloading.
I see. So in this way, you keep the big press busy almost all the time.
That's right. Over here we have some molds which are being assembled and some which have been stripped down to be cleaned, ready for further use.
Is this the largest pressing unit you have?
No, right around the corner we have a 1,000-ton press, which is presently our largest unit. This is used for pressing our largest 9-inch diameter windows. In this case, the mold parts are so heavy we need a hoist to assemble them.
Thank you very much, Dick, for showing us your production facilities. It was fascinating to me to see how you've taken what started as a laboratory process and scaled it up for the continuous production of such large pieces of hot-pressed ceramic material. But I guess now many people will have a question. It's clear that you can make transparent ceramics, but the process looks both complicated and expensive. Now, why on earth should you go to all that trouble when glass is so cheap, so easy to work with, and so very transparent?
Yes, it would be foolish to spend time and money making windows by hot pressing if we could use glass for the same purpose. However, to show you why these materials are valuable and how they are different, let's go next door to our spectrophotometric laboratory. Light is, of course, electromagnetic radiation, and as this chart of the electromagnetic spectra shows, the visible portion occupies a very small part of the entire spectrum. There are no materials which are transparent to all wavelengths in the spectrum, not even air. Many glasses, as you know, are transparent to visible light, but all the simple stable glasses begin to absorb quite strongly at wavelengths longer than the red, that is to say, in the infrared portion of the spectrum. There are indeed a number of single crystal materials which are transparent to the longer infrared wavelengths, but these are very difficult to grow, and it's exceedingly expensive and sometimes impossible to produce these large optically perfect crystals. However, by taking the same compounds and subjecting them to the vacuum hot pressing technique, we can produce large pieces which retain this valuable infrared transparency, and this is the principal reason why we are interested in the vacuum hot pressing process. In fact, we call our product by the trade name IRTRAN, which is short for infrared transmitting. By taking different crystalline starting compounds, we produce a number of different IRTRAN materials, each with a different window in the electromagnetic spectrum. Here are some examples: IRTRAN 1, 6, and 2. The white portion on the chart represents the range where these materials are transparent. Since the range of infrared transmittance in these different materials is critical for many applications, we maintain this spectrophotometric laboratory. Representative samples of every batch are tested for transmittance as a function of wavelength using these infrared recording spectrophotometers.
I suppose that since the main interest is in the infrared region, the visible part of the spectrum may not be quite so important in some applications. Do you make any materials which are opaque in the visible and transmitting in the infrared?
Yes, I have some IRTRAN 6 material right here. It's very transparent in the infrared from 1.5 to 31 microns. However, in the visible, it's totally opaque and it looks black.
Could you give now some examples of the uses of these infrared transmitting ceramics?
Yes. The first is right here in the Hawkeye plant on the 7th floor. It's an infrared laser which uses carbon dioxide gas pumped by an electrical discharge to generate a very intense beam of coherent infrared light at a wavelength of 10.6 microns. The laser works continuously when it is powered and produces a beam with an energy density of 56 watts per square centimeter. To transmit the infrared light out of the laser tube, it is necessary to have lenses and windows which are quite transparent to the infrared at 10.6 microns. Glass windows would be useless for this application and this can be shown quite easily. Although you cannot see the infrared beam, you can see the spot where it is being absorbed by the firebrick beginning to grow red hot. If the glass beaker is now put in, the hot spot immediately fades, showing that the power is being absorbed in the glass. So much energy is being absorbed that it heats up, and if we wait a moment longer, a hole melts through. If the glass is now replaced with Airtran 6 material, which looks quite opaque in the visible, you can see the firebrick again is red hot. This is because Airtran 6 material is transmitting the laser beam.
Well, that shows clearly the advantage of the Airtran material. But what sort of practical applications is it used for?
At present, most of our materials are being used as lenses or windows for the very sensitive infrared detectors which are used to look at radiation from thermal sources. There are both military and commercial applications of this sort. As you know, a number of defensive rocket weapons use heat-seeking systems, which are attracted by the infrared radiation from the hot exhaust of the hostile aircraft or rocket. One example developed by General Dynamics is the red-eye ground-to-air weapon, which uses an Airtran nose dome, which allows the infrared radiation to enter the rocket and to be focused upon the detector which guides the rocket. The rocket is held on a hand launcher and directed at the path of an intruder, in this case a pilotless aircraft entering the picture from the left. As soon as the red eye sees the hot target, it locks onto it and will follow the plane regardless of its course. Our material withstood the laser beam, but of course will not withstand this type of impact.
The infrared system must be very sensitive, judging by the distance of the aircraft when the missile was first launched.
Yes, it's very sensitive. And there are other military applications for infrared in mapping and in search equipment. And I understand that some of it is so sensitive that they can detect the presence of infantry just by their body temperature. In commercial applications, use is also made of the transparency of these new materials to the radiation from hot objects. On the railroads, for example, a well-known hazardous condition can occur if the axle box on the railroad car runs out of grease. The dry box becomes heated by friction, and if undetected, the axle may seize up, needing expensive repairs. It may even cause a train to jump the track. It would be most expensive to mount individual temperature sensors on each axle box. A better solution, developed by General Railway Signal Company, is in use by the Erie-Lackawanna and by many other railroads. Infrared detectors, called wheel thermal scanner units, are mounted at trackside to scan the wheel hubs of passing trains. Any hot boxes are instantly reported to a control office so that remedial action can be taken. This same detection principle has been applied in many other areas. And perhaps one of the most interesting, currently being studied by Barnes Engineering, is the use of infrared to monitor very small changes in skin temperature, which can occur when faults develop in the human circulatory system. Dr. Ernest Wood, director of the Neurological Institute at Columbia Presbyterian Hospital, has shown that an asymmetry in the skin temperature of the face, which shows up clearly on the thermograph, can result from a constriction in the carotid artery, which if left uncorrected could lead to a stroke. There are other methods like the angiograph for detecting this condition, however they require the use of x-rays and injections. And as Dr. Wood states, the thermograph technique is much simpler because it is painless, rapid, and can be repeated as often as necessary for the patient. All he needs to do is just face the detector.
Is it true that the thermograph can also be used in cancer diagnosis?
Yes, doctors tell us that in skin and breast cancers, there's a local disturbance in the circulation, which results in a local change in skin temperature.
I notice that most of your applications are in systems which detect or measure thermal radiation. Is this where most of the interest lies?
This seems to be our experience. However, there are many other applications for these Airtran materials, such as in scientific instruments, like the infrared recording spectrophotometers which we saw a little while ago.
So far, we have talked only about the optical properties of vacuum hot-pressed ceramics. But it would seem to me that this process of densification should provide considerable improvement in many other properties.
I'm sure that it will, and that ceramics produced by this technique will find many new applications in the future. We know that there are high-quality ceramic piezoelectric transducers and capacitors now being made by this technique, and there's considerable interest in hot-pressed electro-optical materials. The elastic properties are certainly better than ceramics formed by conventional techniques, as you know from your own work.
Indeed I do. Now I'd like to thank you, Ed, and your colleagues here at Kodak for all your interesting comments and demonstrations. Now it may be that you are yourself handling materials in industry and have come upon a problem which could benefit from the application of one or another of the many new techniques which are now available. If so, and if you are in need of advice, you may like to talk to the people who are working in the universities, colleges, and technical institutes in Pennsylvania. PENNTAP can put you in touch. Write to PENNTAP.
For more information about PENNTAP, write to 201 Wagner Building, University Park, Pennsylvania, 16802. Looking at Materials is produced for the Pennsylvania Technical Assistance Program with funds provided by the Federal and Commonwealth Departments of Commerce under the Federal State Technical Services Act of 1965.